Hello, everyone. Welcome to the last session, well, the second last session of this conference. We're very glad to have Patricia here to tell us about a resource theory of entanglement with a unique multipartite maximally entangled state.
Hello? Good? Okay. Cool. Well, thank you all for being here and holding out to the last session. And thank you especially to the organizers for putting on such a great event. So I'm going to talk about a resource theory of entanglement of the unique multipartite maximally entangled state. And I like to think that I've kind of given away the talk already because that's the result. And that's kind of like starting a story at the end, much like in Gabriel García Márquez's novel, Chronicle of Our Death Foretold, where, well, it starts with some guy who, well, on the day they were going to kill him, Santiago Nassar got up at 5:30 in the morning to wait for the boat the bishop was coming on. So you immediately know that the guy's going to die, and the whole novel is about reconstructing how and why he died and all of that. So that's exactly what we're going to do. We're going to reconstruct, first of all, why we care about multipartite maximally entangled states, why that's not an obvious thing, and how to arrive at one. And if you're here, I guess you know already that entanglement is kind of cool. Entangled particles can't be written as a tensor product of two different things. And this is interesting because the correlations that it gives rise to allow us to come up with exciting applications. And why is entanglement so cool? Because you can't generate it in separate labs. So it turns out that if you put Alice and Bob in two separate labs, such that they can only do local operations each in their lab and communicate classically, then they can't generate entanglement where there was none. So we call this paradigm LOCC for local operations and classical communication. Entanglement not only can't be generated at a distance, but after the protocols that it's useful for, it's usually consumed. And in this sense, we can say that entanglement is some kind of a resource, right? Because it's difficult to generate and easy to consume. And we can even develop this further into a full-on ordering of the states, so that if, say, for a protocol, you need a given state sigma, but instead you get a different one, you get rho, maybe at a distance, like you can collaborate with your partner and transform rho, the one you're given, into sigma, which is the one you needed. And in this case, we can say that rho is somehow more entangled than sigma because it's more useful. Because everything that you need sigma for, you can use rho for as well. Just you transform it first into sigma, and then you go use it. And so this is what we call a resource theory, where the free states are the states that you get for free, as the name suggests. And in this case, they are the separable states. And the free operations are everything that you're allowed to use just without restriction. So in this case, it would be local operations and classical communication. And everything else, every other state that's not free is called a resource state. And the game that we play with this resource theory business is to order the set of states from the most to the least useful. And we can do this in bipartite entanglement, no problem. And what happens with pure states, at least, is that you get one maximally entangled state, and that's the state we all know and love, and we like it because you can transform it into any other state using LOCC. So that even if you didn't need it for your protocol, well, if you get it, you're done, because you can transform it into whichever state you need, and then perform the protocol. And there's also a very clear relationship between states such that you can transform one state to another if and only if the state you're transforming to majorizes the first state. And I don't care what the maths behind that is, but just to make the point that there's a very clear hierarchy of states with a very clear criterion. Okay, so fine, if we can do it for two parties, let's do it for three, right? We just extend the paradigm. We set up some like classical communication channels between Alice and Bob and Charlie, and we allow them to do LOCC, and this should give rise to a very nice structure, shouldn't it? Well, for a start, what we need to do is to distinguish between the different kinds of entanglement that we get in three parties. Because we can have fully separable states, which are A tensor B tensor C, And those are different from biseparable states, which is things of the form A tensor BC, or B tensor AC, or C tensor AB, or even any convex mixture of those. And that's different again from genuine multipartite entanglement, which is everyone's entangled with everyone. And, well, once here, okay, we've done like the definitional side of things. Should we be able to come up with a hierarchy just like we had before? No. The answer is a lot more complicated because in 3 parties, it's been known since 2000 or so, that there are 2 different classes of genuine multipartite entangled states. And what does this mean? That if I get a state in the GHZ class and I want a state in the W class, I can't get to it, not even if I allow for arbitrarily large error. And this is quite bad because, well, we can't like order the set of states in any which way, but we might think that we can order each group of states, right? Each class. We can order everything in the GHZ class and then everything in the W class, and we can't compare between them, but okay, at least we've done something. Well, it turns out that's not possible either, because there's this phenomenon called isolation. So there are some states from which you can't get to any other using LOCC, and to which you can't get from any other using LOCC. So if you're given that state and you needed another one, you're stuck. And if you're given a different state but you needed that one, you're stuck as well. So that in particular means that we can't order each class of states. Well, still, for more than 3 qubits or for dimension larger than 3, isolation is generic. So not only can you order the states because you have like a few outliers, the outliers are the majority of your states. So, okay, there's no hope of ordering anything. Can we come up with a different resource theory, maybe, with a maximally entangled state of 3 qubits? And if you read the title, maybe you know already that yes, we can. But the game we're playing here in the talk is that we're gonna like try and motivate why, like how we're gonna find this resource theory, right? So for a start, what could we do? What parameters in the resource theory can we change? Well, one thing we can do is increase the set of allowed operations. So it turns out that LOCC isn't the largest class that leaves the set of separable states invariant. So you can do more than LOCC. Forget about the physical interpretation, we'll come back to that in a minute. But mathematically, you can do more than LOCC and still have a closed set of separable states. Be that the fully separable or the biseparable or the separable in 2 parties, whatever, but we can expand that in that way. And we definitely want to leave the set of separable states invariant, because otherwise, if we can create entanglement where there is none, then, well, the like correlations motivation kind of goes away, right? Because if I can have those motivations for free, my resource theory kind of loses appeal somehow. So okay, just coming back to the physical interpretation deal briefly, the reason I'm not too worried about it is because, well, if with the physical interpretation I can't do anything at all, then at least mathematically I can hope to get something done and then find the operational interpretation later. And, well, this has been done before, like in the resource theory of coherence, if you've heard about that before. So for now, we're just going to focus on the like structure that we can arrive at mathematically and worry about the physics side of things here later. So, okay, we're going to generalize and we're going to allow for any false probability preserving operation. And what does this mean? This means that, well, as you can see, there are no like envelopes and local things. This is just kind of more abstract. And I allow any operation that leaves me within the green set of states. So we say lambda, a map, is full separability preserving if and only if for every fully separable input, I get a fully separable output, as the term suggests. Okay, so what structure does this give? Let's recall what we had with LOCC, this business with the 2 different classes of states and the like huge brick wall between them, and then a few isolated states there. Well, in full separability preserving operations, we don't have any inequivalent entanglement, so we don't, probabilistically, we can go from any state to any other state. And that's kind of nice, because that at least allows us to have a non-trivial theory, and we also don't have any isolation. So if you give me one state, I can always give you a map and a different state, so that I can go from your state to mine. And, well, as a few like extra bits, we can go from the GHZ state to some states in the W class deterministically, and vice versa, from W to some states in the GHZ class deterministically. That's kind of nice. And let's just see this formalism a bit more. So we have one theorem that says that there are no SLOCC classes, which are the types of entanglement that I mentioned before. And what this means is that all resource states, so all like non-fully separable states, are interconvertible with non-zero probability. So if you give me any two states that aren't fully separable, I can find you a map such that I can go from psi1 to psi2 with a given probability p that's different from 0. All right, that's kind of nice. Further, we don't have any isolation anymore, so that given one state, I can find you a different one and a map such that I can go from psi1 to psi2 deterministically. Okay. However, we still haven't arrived at the promised result because we don't have a maximally entangled state, at least in 3 qubits. And we have only been able to prove this for 3 qubits, and I'll go into more details about this at the end. So, okay, can we do better? And again, if you read the title, you might be already knowing that the answer is yes. Well, you can see how we're going to do that maybe. Before we left the green set invariant, now we're going to leave the blue set invariant. So we're going to allow any operation such that for a biseparable input gives me a biseparable output. So now my free states are huge. They're all biseparable states. And these are all pure states that are biseparable and all of their convex mixtures across all different bipartitions. And so my resource states are the GME states, the genuine multipartite entangled states. Okay, so this is kind of what it looks like. And what structure does this give rise to? Well, again, recall what it was like for LOCC. This time, we're going to be able to go from the GHZ state to any other state, deterministically. We found it. We have a maximally entangled state, and it is the GHZ state. And so the W class just doesn't make sense anymore because you can go deterministically to any state in that class from the GHZ state. And further, we need to talk about classes of states rather than states themselves, and I've been kind of implying this throughout the talk, because the ordering needs to be well defined. So in particular, because I can freely go back and forth between any two states in that blue ring, I need to say that that's just the one equivalence class of states, just so the structure is well defined. So the picture looks like this now, and again, if I have a class of biseparable states, a class of free states that's like one single element in that class, just like that, I also have a class of maximally entangled states, and because this is valid for n qubits, so for any number of particles in any dimension, it turns out that that not only the GHZ is in that class, also all graph states and even more states are in that class. And this is starting to look a little nice because we know that graph states are useful. We like them for quantum computation and stuff. So, so this gives us hope that this whole thing makes sense, basically. And we also keep the results that we had from the full separability preserving paradigm. We keep the no inequivalent entanglement and the no isolation, and the proof just goes through in the same way. And just for you to see the theorem, there exists a maximally GME state on every Hilbert space. So for fixed dimension and fixed number of parties, I can give you a map that gets you from the GHZ state to any state that you give me. Good. Okay, so now I'd like to give a brief idea of how we arrived at the results, not so we get like confused about the maths, but rather so you get a feel for the techniques that we've been using throughout the paper. And while we don't have a general characterization of the biseparability preserving maps, we do have some examples, and this is one of them. So we're going to spend a bit of time staring at this map. As you can see, it's a mixture of a state psi and a state rho bs, because the coefficients are numbers. And so what happens, so this lambda of chi, when I input chi, I get out some kind of convex mixture of psi and some biseparable noise. And so if there's a lot of biseparable noise, then the output of the map will be biseparable. And if there's not a lot of noise and psi was genuine multipartite entangled, then obviously the output will be genuine multipartite entangled. So the game is like, how big can this S be? And this is exactly what the definition of the robustness is, which is a measure of entanglement. So so it's the minimum S such that the output of this map is is separable, or bi-separable in this case. So what do I do with my input? Where did that go? I multiplied it by GHZ, and I took the trace, so that gave me a number. And so what we're going to do is try and relate this number, this trace of GHZ with my input, to the robustness of the state psi. So in particular, if the input is bi-separable, then the output will also be bi-separable if the inequality that's on the board holds. So if the trace of GHZ chi is smaller than or equal to 1 over 1 plus the robustness. And the reason the robustness is not just, is you need to add 1 and take the inverse, is so that the output of the map is normalized. Okay, so we have the criterion that we want. How do you go about this? It turns out that the maximum of this trace is 1 over d's, because you can relate, well, this trace is actually the geometric measure of entanglement of the GHZ state, and that you can work out in terms of the eigenvalues, the largest eigenvalue across all possible bipartitions, and this is equal to 1 over d. And also we can relate the robustness of psi to the dimension, and it turns out to be always lower than or equal to d minus 1. And so if you plug the numbers in, you see that the inequality holds all the time for all d and independently of n. So we're happy, and we found a maximally entangled state. And so this is roughly how the proof goes. And now you might be wondering, well, okay, if the proof was so nice for the by-separability case, why is it not equally nice for the full separability case, right? Like, what happened? Well, it turns out that the measures of entanglement aren't defined in the same way, and they're not so nice for full separability preserving operations. So in particular, the same tricks with the eigenvalues don't hold, and we need to pick whichever entanglement measure doesn't increase under the free operations, and those are called entanglement monotones. And because they are dependent on the free operations, they might be defined differently for bi-separability and full separability preserving operations. And so we have a criterion if we pick one of these measures, so that if the measure of phi is lower, strictly lower than the measure of psi, then I know I can't go from phi to psi. And so it turns out that the geometric measure, whatever that is, but it's a monotone, of the W state is strictly larger than the geometric measure of any other state. And that's great news, because that means that the W is the only candidate for the maximally entangled state. It doesn't mean that it is the maximally entangled state, it just means that if there is one, it's that one. Because I can't go to the W from any other state. Okay, so our hope was, fine, pick a different monotone, get the opposite inequality, so get that the entanglement of W is strictly lower than the entanglement of a different state according to that measure, and be done with it, because that would mean that we couldn't have a maximally entangled state. But we decided to pick the robustness, and after a lot of playing around, we found that it was exactly equal to that of the GHZ, which was the other obvious candidate for a maximally entangled state. So we gained no new information, and we were very sad. But along the way, because the robustness took a while to compute, we'd gained quite a lot of insight. And so we found an obstruction to the map that would take the W to the GHZ state. And what does that mean? If you can't go from your only candidate maximally entangled state to another particular state, it means that it can't be the maximally entangled state by definition. So we've proved that there is no maximally entangled state of 3 qubits. And why is this result so general? Because we deliberately picked the largest class of operations that made for a non-trivial theory. So if there's no maximally entangled state in this theory, there's no maximally entangled state for any theory that has the fully separable states as free states. Okay. So what have we done so far? We've observed that the LOCC, the resource theory of LOCC in the bipartite pure case is very nice, because we have the one maximally entangled state and everything follows from there. It is really not so nice in the tripartite case, and in fact, when the number of particles or the dimension is larger than 3, this is generically trivial, so we can't really do anything with LOCC in more than 2 parties. So we decided to expand our class of operations and found that full separability preserving theories or operations give rise to a resource theory that's nicer, but still not as nice as it could be, because it's non-trivial, but we don't have a maximally entangled state, at least in the 3 qubit case. And then we expanded our class of operations further and took the largest class that preserves the set of bi-separable states. And so we found a unique class of multipartite maximally entangled states. And so now we want to know whether this is physically meaningful at all, whether we've been wasting our time so far, and well, there's hope, because the applications of the maximally entangled BSP states are there, they're graph states, and they're useful for computation, and so on. And we'd also like to know whether the resources required to implement by-separability preserving operations are fewer than just global unitaries, because then, well, that means that our theory is somehow operationally more motivated than it was before. And maybe you're wondering how this book ends Chronicle of Our Death Foretold, given that it seems to finish at the end. And here's the quote. And well, he stumbled on the last step, but he got up at once, you know. Then he went into his house through the back door that had been opened since 6 and fell on his face in the kitchen. So I hope you enjoyed the chronicle of a multipartite, maximally entangled state foretold. Thank you.
Is there any questions for the speaker?
So for bipartite case, separability preserving map includes swap, so this can create entanglement.
Sorry, could you say that again? Sorry.
So for bipartite case,
Yeah.
separability preserving map
Yeah.
includes swap operation.
Yes.
So this can, in this sense, this can create entanglement if it is applied to auxiliary system.
Yeah.
So, and my question is, how about this fully separable preserving and by-separability preserving map?
Wait a second. So anything that can create entanglement is not allowed. So we define the full separability preserving operations as anything that can't create entanglement where there was none. So you start with like 0, 0, 0, and you go to anything that's of the form 0, 0, 0, or of the form like A tensor B tensor C.
If I understand correctly, fully separability preserving map includes swap, right?
It can, yeah, but if...
So yeah, if a party locally creates pair, then performing swap, this creates entanglement. If it is applied to...
What we can't use is ancillas, if that's what you're asking.
Auxiliary system is allowed. So how about by-separability preserving map? That's my question.
Sure, you could, in principle, have the same, but I'm not really sure I understand the question well, because maybe what I didn't mention is that you can't use ancillas in this theory, so you can't like swap with your ancilla. If you have like an extra qubit that's like biseparable, that's outside of your system, you can't swap with it. You can't do anything because that does create entanglement. Is that what you mean?
Okay, so in your definition, using auxiliary system is not allowed.
Using extra systems is not allowed, no.
Okay, thank you.
Yeah. Just because it creates entanglement, there's no other like reason that impedes that, yeah.
Hi. That's a very lovely talk. I have lots of questions over here.
Oh, hi.
Hi. But the one I'll ask you just now, and maybe I'll catch you later, is have you thought about doing this as the kind of an asymptotic resource theory, where you talk about, you have an n GHZ states, how many other states can I transfer
Yeah,
them in?
so the problem is that you can't use ancillas. So if are you referring to the results by Brandau and Gore and Plenio? Is that the papers that you're referring to?
No,
Or
just
are you just like
in general for a resource theory, this is sort of a one-shot resource theory where you can go from one GHZ state to one state.
Sure.
Typically in resource theories, you want to talk about a value of the resource and having many copies of it in one.
Yeah, so we tried that and it didn't work, just because you can't have the extra system. So the set of free states isn't closed under tensoring many copies. So for example, if you have a mixed state that's maximally entangled in Alice and Bob, tensor 0 for Charlie, plus 0 for Alice, tensor maximally entangled for Bob Charlie, and you tensor 2 copies of that, well, 1 copy is biseparable, but 2 copies aren't. So the set of free states is a bit kind of odd, and that is an impediment to doing an asymptotic version.
Okay, that's interesting.
Yeah, it was an observation that took us surprisingly long to like realize, and then we're like, oh, well, that's the end of that then.
It might not be the total end of it. There are other games you can play.
Okay, sure, I'd be happy to discuss further then, yeah.
Absolutely.
All right, unfortunately, we're out of time. Let's thank our speaker again.
Thank you.